So my name's Arul Verma, and this week we're going to be going over borrowing and ownership in CS128 honors. Excuse me if I cough in the middle or if I slow down. I'm a little under the weather, so please bear with me. So let's start by talking about what ownership is. So ownership is a concept implemented and exclusive to Rust, and it's a form of memory management protection. And it's done using a system of rules that are checked at compiled. So these are the three key rules of ownership that Rust follows. The first is that each value in Rust has exactly one owner. There can only be one owner at any given time. And when the owner goes out of scope, the value of that is stored is dropped or freed. So in this case, let's take a look at what we have here for let s equals hello. So we can see that s is not yet valid prior to its declaration, which is obviously true. We can't say, we can't do anything with s. We can't print s before we declare s. And when we declare s with let s equals hello, s enters the scope. So we can see that the value comes into existence and s is the owner of the data hello. From there, we can do whatever we want with s. And when we do the close parentheses, s goes out of scope. And that's what we mean by scope. Scope is just the set of braces that you exist within, curly braces you exist within. And this is a very familiar concept to anyone who's programmed in C++, Rust, Java, Python, any language really that implements scope. But Rust takes this a step further, and we'll talk about it right now. So for Rust, scope is slightly different because Rust doesn't only check scope at the curly braces existence. So in C++ or Java, for example, if we were to have a program like let s equals hello, and we do stuff with s, say this declaration was int main. So that just means the main function. For Java, it would be your main as well. And so s would be in scope for the entirety of the function. It would exist all the way up into the end of the curly braces. However, Rust, the definition of scope is slightly more complex because Rust, as in its compile time, it checks to see the last usage of a variable. And the reason Rust can do this is because of how it handles memory. And we'll go into that in a second. But basically, what you have to understand is with other programming languages, this isn't very doable because other programming languages like C++, C, Java, Python, they give you some access to the memory side of things. There's no hard and fast rule set like ownership. So because of that, there can be interesting scenarios where you set two objects equal to the same point in memory. And we've kind of alluded to this earlier as well, that like memory is slightly more complex. So if we have two variables pointing to the same space in memory with other languages, then if we try and delete one of them and take it out of scope, the memory that it's pointing to is deleted. And actually, before I give this explanation, perhaps I should explain a little bit more how memory works for people who aren't as well acquainted. So the way I like to think of memory is as an address box or like a PO box. So say you have some sort of data. So this variable s in let s equals hello, s has its own PO box where it can store data. So there's some arbitrary number which we'll write down as 4258763. And these are just arbitrary numbers that I came up with. So at box 4258763 in memory, so this is that box that this address points to. So before this, we have 4256762. So this would be 4256762. And after that, you'd have 4256764. And you get the point. I'm not going to write it out. But at this particular box, we have hello. So whenever we want to access whatever's in S, we go to the corresponding PO box, the address, and we look inside that address to get the string hello. Of course, this is slightly more complex because with strings, you don't just store the entirety of hello. In reality, what you do is you store the H here, the E here, the L, and the O, one in each box. And with strings, you know to keep looking until you see a null character, which would be our termination, which is /0. So that's actually how memory works. So now that we've gotten that out of the way and you understand kind of how memory works, now let's go back to what we were talking about before, which is that we have our let s equals hello. And with other programming languages, we could also do something like, which we'll see on the next screen, let s1 equal s. And the problem is that In that point in memory that S has stored 425, whatever it was, 762 or 763, S1 would also be pointing to that exact same address space because we've told it that, hey, forget your original PO box. Go store the same PO box, go to the data at the same PO box as S. So if we delete S and we delete that entire hello, then S1 will also not have data. It'll be pointing at nothing. But Rust ownership concepts prevent this from happening because ownership inherently prevents the situation from happening. So the compiler at runtime will go through and make sure you're not violating any of these concepts. So when you're running it, the code already knows that there's no situation possible where there's going to be S pointing at a null character or pointing at something that doesn't exist. So because of that, Rust can check scope and it can end an object scope at the last usage in the code. So what I mean by this is we see let I1 equals U in I1, right? And let I2 equals U in I2 versus I2. So if we were to check here what's in scope, in other programming languages, after these curly braces, only I1 would be in scope because I2 existed in scope between these two curly braces, and then it went out of scope, which makes sense in every programming language. But over here, I1 should in theory still be in scope because it's still within the curly braces of main. But in reality, what has happened is Rust has said this is the last usage of I1 ever. So it's out of scope after this line. And the way the compiler checks this is a rule set called non-lexical lifetimes. I just thought this was a really cool piece of information. You don't actually need to know the name of this rule set, but if you want to search it up, make sure you do. It's really, really cool. And it's very interesting how the compiler can check to see when an object is last used. So we talked a lot about like how memory works, a little bit about like what it kind of does. So now we're going to go more in depth into why we need that memory protection. So for those of you familiar with how memory is, you'd already know there's two types of memory: heap memory and stack memory. So stack memory is what we call short-term memory. It's generally smaller in size, but it's faster to access. So when you don't explicitly declare new or delete, you're accessing and editing your stack memory. Data is automatically placed on your stack, and your user doesn't have to allocate custom amounts of memory. So free, delete, malloc, new, all of those work with the next type of memory we're talking about, which is heap. And this is our long-term memory. It's much larger in size, but it's also much slower to access. So the user must declare the amount of memory they want to allocate per object because heap, there actually isn't an infinite amount of heap memory. There's a lot compared to the stack for sure, but it's also not a lot of memory overall. So you want to be very careful about managing your memory. And that's also why Rust gives you those I8s, U8s that we talked about earlier, giving you custom access to the memory size of your variables because you don't actually have a lot of memory. And it's very important to optimize your usage. Now, the thing with the heap is because it's long term, when you have to declare to allocate, you also have to declare an explicit deallocation. So if you were to use ints in any language, you don't have to free your int or delete your int. But if you were to use something custom like vector or string, those also you don't actually have to handle in C++ because of how it handles garbage collection or in Java. But if you use pointers, any form of pointer memory, void pointers, char pointers, so a string is essentially just a char pointer. Especially if you're doing this in C, you'd have to explicitly deallocate that memory to prevent a leakage. And this is super, super important because Valgrind is run on code, and that's how we check for memory leakage. So if you have memory leaks, that means that you're not freeing your memory somewhere. You're not properly dealing with the garbage in your code, like the garbage pointers that you've already finished using. So if you're familiar with Java, you'll realize that you've never actually had to deal with freeing your memory. And that's because Java has something called garbage collection. And what this is essentially at runtime, while the code is running, a daemon thread, which just means an automatically run thread, determines which memory is unused and automatically deletes it. And how it does this is it just goes in and sees the last time that memory is accessed. And if it hasn't been accessed in around 2 or 3 cycles, it just automatically deletes the code. So it's the data. And this is good and bad. It's good in the sense that it reduces the need on the programmer to delete any form of like memory storage and memory like processing. So you don't the programmer doesn't have to deal with the memory side of things. but it's slow. And this is why Java isn't used for high performance computing because it is slow. Automatic daemon collection, garbage collection with a daemon thread is essentially it's a drain on resources. And you might be asking why C and C++ don't implement a garbage collection because it seems like a good idea. But with pointers and references, it's actually impossible to have an automated garbage collection. And this is an example of why. So here we have string s2, and we create a new string with explicit keyword new, so we allocate memory in the heap. And then we have a string s3 that we set equal to s2. So this is just us saying like, okay, inside my address, so s3 is going to have the same address as s2. That's all we're really saying here. So for those of you not familiar with C++, actually I should probably start from the beginning. What this is doing when we say string star is instead of declaring a string, we're saying this is our address in memory, our address box, and that address box is going to contain a string. And here with string star s3, we're saying now s3's address box is the same as s2's address box. So when we say delete s2, what we're actually telling the compiler is go to that address box of s2 and delete everything that you see up until the end of the string. So this entire hello is deleted. So if we were to visualize this, what's actually happening is we have our box here. And this is storing HELLO, and this is storing our null character, which is our end of string. And S2 points here. And now S3 points to S2, which also points here. Now, once we do this line delete S2, we're taking an eraser and we're erasing everything. And now when we try and print S3 here, we're going to get an error because S3 is pointing at nothing. There's nothing here. We've deleted it. So this is empty, 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 and this is empty. And this code would crash. So this is the reason why pointers don't really work well with garbage collection. Because if we have an automatic deletion, the compiler can't tell if we have two pointers pointing to the same space in memory. So S2 might not be being used again, sure, but S3 is being used again. So the compiler can't tell. It's like, oh, S2's not been used for so long, no one's accessing it. Let's just delete it. No harm done, right? But S3 has a problem with it because S3 is pointing at S2. So pointers and references make garbage collection fundamentally impossible. And that's why in Java, you never actually see the star or the ampersand. You don't have to deal with them because Java doesn't give support for those things. But in C, C++, and Rust, languages that do give you access to memory, like low-level memory with star and ampersand, you'll realize that you can't have garbage collection. So Rust bypasses these, like the check on the user without forcing the user to actually manage memory by implementing ownership and using the ownership rules. So it does this with a concept called borrowing. So the concept of ownership is that, as we said, only one person can own the data, right? Only one person can own the original value. So then that brings up an interesting question. If only one person can own the data, in this case, when we declare s1 equals string from hello, only s1 owns the data. So when we do let s2 equals s1, that's valid code. That's something we can do. So why and how can we do it? What makes it work? Well, the concept of borrowing is that we can borrow data from the original owner. So much in the same way that like I can borrow an apple from Neil or you can borrow an apple from your roommate. It's much in the same that like when you borrow it, you take it from them. But unlike borrowing, as the word implies, you don't give it back. So without borrowing, without the concept of borrowing, in C++, you'd have both S1 and S2 pointing to our memory of hello. But with Rust borrowing, what happens is S1 is immediately freed. It's removed from memory and it's treated as deleted. So if I were to do this println of world S1, this would crash. Rust would not let this code compile because S1, as far as the compiler is concerned, does not exist anymore. So we're only worried about S2. The only thing the compiler considers is S2. So S2 is the only one pointing to hello. And this is the correct way of how Rust deals with borrowing. So like with all rules, there are exceptions. Borrowing isn't a universal, oh, whenever we're trying to set equivalence, the first one is deleted. So, oh, sorry about that. So anything stored on the stack has an implicitly allocated or created copy trait. So all of your integers, unsigned integers, bools, characters, they all pre-implement a copy trait that you don't see or deal with. But whenever you try and use the equal sign with an integer, a boolean, a character, or a tuple, they automatically use that copy trait. So what's actually happening, say, instead of this as being a string, say this was an integer. So let s1 equal 2, let s2 equals s1. What's happening is s1 gets that 2, and then s2 gets a new 2 in a separate place in memory. And it would look something like this on the right, well, sorry about that. This is like still using the string example, but say this was like using our integer example. Instead of getting hello here, this would be like a 2, and s2 would get its own separate 2 in memory. So this is how it would look. And we'll come back to the slide to explain cloning a bit, but I just want to go a little bit more in depth on the copy trait. So yeah, so as you can see, like copy is specific to a lot of your stack data stuff. So strings are not something that you can use copy for. Vectors are not something you can use copy for. They're purely for things like that are static data types. Uints, ints, bools, characters, floats. And tuples also can implement copy, but they're only copyable if both of the types in your tuple also implement copy. So you can do I32, I32, but you cannot do I32 in string. So now let's talk about cloning. So say we want both S1 and S2 as variables we can access. Give me 1 second. All right. So yeah, say we want both S1 and S2 as variables we can access. So then we can do something called clones. So clones are a built-in function for almost all classes in Rust, which completely copies all data. And what we mean by that is say you had multiple types, such as storing your pointer in memory, your length, and your capacity. Then you copy all of this. You don't just copy the data, the hello. And that's something that we call a deep copy in programming, where you copy all the data in a class instead of just the like one part of the data that's being stored. So clones are built in for strings, and this is a semantic that you have to understand. The clones and copies are not the same. Copies fundamentally do a very shallow copy. They only copy the data, but clones copy everything. So, and they like make a whole new clone that's identical to the first. So if we were to do S1 and S2, we'd both get separate hellos. And this is where like this type of thing in memory happens, where we have S1 existing on its own and S2 existing on its own, and this is what would be the end result of a clone call. So the copy function is an implicit function call. You don't actually call dot copy, especially if you're using like an integer or an unsigned integer. You don't have to say dot copy. Once you use the equal sign, the copy construct or the copy function is already called, and it can create a shadow copy or it can simply move the memory, but it doesn't create a deep copy of the object, not necessarily. And it uses the memcopy function, which is something that you can search up in Rust docs. Essentially, all you need to know is that it copies over the data in memory to another space in memory. However, dot clone is always an explicit function call. You can't dot clone with an equal sign. You have to use the dot clone function, as we can see here at this fact. And it's always a deep copy, and it can do arbitrarily complex operations to create new objects. So we can see that like if we had to have this, v equals vec, and then w equals clone, it creates a new vector for you. It makes them all unsigned integers of size 8, and then it adds everything. And we can see that this is with the vec macro, so you can use the vec macro as well. So not all functions implement clone or copy, or sorry, not all classes implement clone or copy. So it may be necessary sometimes for you to create them. And we do at one point in this class ask you to implement a clone and a copy function for a class. So get an understanding of the difference between shallow and deep copies because it will be important. We can see here that like what uses clone and what implements copy, and also the concepts of move. We can see like W equals V. This is what would be like a borrow, so a move essentially, and it would render V unusable because V would have been freed. So yeah, that's an overview of how borrowing and ownership works. We're going to go much more in depth over the next two lectures. I know this was super fast, but this is just meant to get you familiarized with the concept of borrowing and ownership, and we'll give you a better understanding hopefully over the next week. All right, that's everything for today. If you want to follow along, these are in the Rust lecture docs. There is a entire chapter on borrowing and ownership. So make sure to read that if you want to read the documents. Yeah, so that's everything for this week.